Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Upon graduating from Yale in 1930, Mac Lane embarked on a transformative period of study at the University of Göttingen, Germany. Göttingen, at the time, stood as one of the world's preeminent centers for mathematical research, attracting leading scholars from across the globe. There, Mac Lane encountered luminaries such as Emmy Noether, Richard Courant, and Paul Bernays. Noether, in particular, exerted a profound influence on Mac Lane's mathematical development. Her groundbreaking work in abstract algebra, especially her axiomatic treatment of ring theory, exemplified the power of structural thinking in mathematics. Mac Lane absorbed Noether's ideas, internalizing her emphasis on the intrinsic properties of mathematical objects rather than their specific representations. The political climate in Germany during the early 1930s grew increasingly turbulent with the rise of Nazism. Mac Lane witnessed firsthand the growing anti-Semitism and the erosion of academic freedom. This experience profoundly affected him, reinforcing his commitment to intellectual integrity and social justice. In 1931, he earned his master's degree from Göttingen. With the deteriorating political situation, Mac Lane made the decision to return to the United States. He completed his doctoral studies at the University of Chicago under the supervision of Leonard Dickson, a prominent algebraist known for his work on finite fields and linear groups. Mac Lane's dissertation, completed in 1934, focused on the axiomatization of field theory, reflecting his growing interest in the foundations of algebraic structures. Following the completion of his doctorate, Mac Lane held positions at Harvard University and Cornell University before joining the faculty of the University of Chicago in 1947, where he would remain for the rest of his career. At Chicago, he built a thriving research group and mentored generations of mathematicians. His impact extended far beyond his own research, shaping the direction of mathematical inquiry both at Chicago and throughout the broader mathematical community. Mac Lane's early work centered on areas such as valuation theory and field theory, contributing to the development of abstract algebra. However, his intellectual trajectory soon led him to confront a significant challenge within algebraic topology, a field that combines algebraic methods with topological concepts to study the properties of spaces and their mappings. Algebraic topology, while powerful, often lacked a sufficiently rigorous and general framework for comparing different algebraic structures and the relationships between them. The existing tools proved inadequate for capturing the essence of certain fundamental constructions, such as the relationships between homology groups in different topological spaces. This limitation became particularly apparent when dealing with natural transformations, mappings between functors that preserve the underlying structure of the mathematical objects involved. The problem, in essence, was a lack of a suitable language for expressing the structural similarities and differences between mathematical objects in a precise and categorical way. Mathematicians needed a framework that would allow them to move beyond the specific details of particular constructions and focus on the underlying patterns and relationships. Mac Lane recognized this need and began to explore new approaches to formalizing mathematical structures. He sought a way to capture the essence of mathematical objects and their relationships in a manner that was both rigorous and general. This quest would ultimately lead him, in collaboration with Samuel Eilenberg, to the creation of category theory, a revolutionary approach to mathematics that provides a unifying language for describing mathematical structures and their relationships. Category theory offers a high-level perspective, focusing on the morphisms, or structure-preserving maps, between objects rather than on the internal details of the objects themselves. This abstract viewpoint allows mathematicians to identify common patterns and structures across seemingly disparate areas of mathematics, revealing deep connections and simplifying complex arguments. While category theory would become Mac Lane's most enduring legacy, its genesis lay in his early engagement with the challenges of algebraic topology and his unwavering commitment to rigor and abstraction. The initial seeds were sown in his formative years, nurtured by the intellectual ferment of Göttingen and cultivated through his early research in algebra and topology. His work was a response to a perceived need for greater clarity and precision in the language of mathematics, a language capable of capturing the essence of mathematical structures and their interrelationships. Mac Lane's trajectory led him to a pivotal collaboration, one that would forever alter the landscape of mathematics. Working alongside Samuel Eilenberg, he embarked on a quest to codify and generalize the tools of algebraic topology. This partnership, forged in the crucible of shared intellectual curiosity, gave rise to category theory, a framework poised to reshape mathematical thought. Algebraic topology, in the mid-20th century, grappled with increasingly intricate structures. One central challenge lay in understanding the relationships between different topological invariants, algebraic objects such as groups or rings, assigned to topological spaces to capture their essential features. These invariants, while powerful tools for distinguishing topological spaces, often required complex and ad hoc constructions when comparing invariants derived from different sources or perspectives. This complexity obscured the underlying unity of many topological phenomena. A particularly vexing problem involved the notion of naturality. Mathematicians frequently encountered situations where constructions were natural in a vague, intuitive sense. Consider, for example, the Hurwitz homomorphism, a map connecting the homotopy groups of a topological space to its homology groups. While the homomorphism itself was well defined, the existing mathematical language lacked the precision to formally express its naturality. The idea that this map behaved consistently across different spaces and constructions, respecting the underlying topological structure. The challenge was to move beyond intuitive notions and provide a rigorous general definition of what it meant for such transformations to be natural. Eilenberg and Mac Lane recognized that the existing mathematical framework, primarily focused on sets and their elements, was inadequate for capturing the essence of these natural relationships. They sought a higher-level perspective, one that emphasized the relationships between mathematical structures rather than the internal details of those structures. This ambition led them to the conceptualization of categories, functors, and natural transformations. A category, in their formulation, consists of objects and morphisms. Objects can be anything: sets, groups, topological spaces, or even other categories. Morphisms are the arrows connecting these objects, representing structure-preserving maps. For example, in the category of sets, the objects are sets and the morphisms are functions. In the category of groups, the objects are groups and the morphisms are group homomorphisms. Crucially, morphisms can be composed, much like functions, and this composition must satisfy certain associativity and identity laws. This simple yet powerful definition provides a framework for abstracting away the specific details of mathematical objects and focusing on their interrelationships. Functors take this abstraction a step further. A functor is a mapping between categories. It sends objects in one category to objects in another category, and morphisms in the first category to morphisms in the second category, preserving the structure of the categories. There exist covariant functors which preserve the direction of the morphisms and contravariant functors which reverse the direction of the morphisms. Functors allow mathematicians to relate different categories to each other, revealing deep connections between seemingly disparate areas of mathematics. For example, The fundamental group is a functor from the category of topological spaces to the category of groups. It assigns to each topological space its fundamental group, and to each continuous map between topological spaces a group homomorphism between their fundamental groups. The final piece of the puzzle, and perhaps the most innovative, was the concept of natural transformations. A natural transformation is a mapping between functors. Suppose one has two functors, phi and g, from a category C to a category D. A natural transformation alpha from F to G assigns to each object x in C a morphism alpha sub x from F of x to G of x in D, such that a certain diagram commutes for every morphism F in C. This commutativity condition captures the intuitive notion of naturality. It ensures that the transformation alpha behaves consistently across different objects and morphisms, respecting the underlying structure of the categories. The Hurewicz homomorphism, for instance, can be formally defined as a natural transformation between the homotopy functor and the homology functor. This definition provides a rigorous and general way to express the naturality of the Hurewicz homomorphism, resolving a long-standing problem in algebraic topology. Consider a specific illustration. Let top be the category of topological spaces and continuous maps, and let ab be the category of abelian groups and group homomorphisms. The nth homology group, denoted H sub n, and the nth homotopy group, denoted P sub n, can each be viewed as functors from top to ab. The Hurewicz homomorphism, T, is then a family of homomorphisms H sub x, one for each topological space x, mapping from pi sub n of x to H sub n of x. The naturality of H is expressed by the requirement that for any continuous map f from x to y, the following diagram commutes: pi sub n of x, mapping to H sub n of x, via H sub x, and pi sub n of x, mapping to pi sub n of y, via pi sub n of f, and pi sub n of y, mapping to H sub n of y, via H sub n of x. This diagrammatic representation, a hallmark of category theory, succinctly captures the essence of naturality. The introduction of category theory was initially met with a mixture of enthusiasm and skepticism. Some mathematicians, steeped in the traditional set-theoretic approach, viewed category theory as excessively abstract and lacking in concrete applications. They questioned the value of focusing on morphisms rather than on the elements of sets. Others, however, quickly recognized the power and elegance of the categorical framework. They saw it as a unifying language that could simplify complex arguments, reveal hidden connections, and guide the development of new mathematical theories. The initial impact of category theory was most pronounced in algebraic topology and homological algebra. The categorical perspective provided a new way to organize and understand the burgeoning results in these fields. It led to more concise and elegant proofs, and it suggested new directions for research. The abstract language of category theory made it possible to formulate and solve problems that were previously intractable. It offered a powerful lens through which to view mathematical structures, revealing their underlying unity and simplifying their complexities. The categorical perspective quickly permeated algebraic topology and homological algebra, offering a novel lens for organizing and comprehending the expanding body of knowledge within these domains. This viewpoint facilitated more succinct and refined proofs, suggesting avenues for future exploration. The abstract vocabulary of category theory enabled the formulation and resolution of previously insurmountable problems. It presented a potent means of examining mathematical structures, unveiling their fundamental unity and streamlining their intricacies. Saunders Mac Lane played a pivotal role in the development of homological algebra, a field that explores algebraic structures through the lens of homology. Homology, in its essence, is a method for associating a sequence of algebraic objects, typically abelian groups or modules, to other mathematical objects, such as topological spaces. These sequences, known as homology groups, encode important information about the structure of the original object. The challenge lay in systematically extracting and interpreting this information in a way that could be generalized across diverse mathematical contexts. Mac Lane, alongside Samuel Eilenberg, recognized the potential of category theory to provide a unifying framework for homological algebra. Their groundbreaking work in the 1940s laid the foundations for the field, introducing key concepts and techniques that remain central to the subject. A central idea was the notion of functors, which are mappings between categories that preserve the structure of the categories. In the context of homological algebra, functors could be used to relate the homology groups of different objects, providing a powerful tool for comparing and contrasting their algebraic properties. Specifically, Mac Lane and Eilenberg introduced the concept of abelian categories, which are categories that possess properties similar to those of abelian groups. In an abelian category, one can define kernels, cokenals, images, and copanages, which are essential for constructing homology sequences. The introduction of abelian categories provided a general setting for homological algebra, allowing mathematicians to study homology in a wide range of algebraic and topological contexts. An innovative aspect of Mac Lane's approach was his emphasis on the use of diagrams to represent algebraic relationships. Diagrams in this context are graphical representations of objects and morphisms in a category. By carefully constructing and analyzing diagrams, Mac Lane was able to prove important theorems in homological algebra in a visually intuitive way. This diagrammatic approach became a hallmark of Mac Lane's work and influenced many subsequent researchers in the field. Mac Lane's contributions to homological algebra extended beyond the development of the basic framework. He also made significant advances in the study of specific homological invariants, such as ext and tor. Ext, short for extension, measures the extent to which one module can be extended by another. Tor, short for torsion, measures the torsion in the tensor product of two modules. These invariants provide valuable information about the structure of modules and their relationships to each other. Mac Lane developed computational techniques for calculating ext and tor, making them accessible to a wider range of mathematicians. His work on these invariants had a significant impact on the development of algebraic number theory and algebraic geometry, where they are used to study the arithmetic and geometric properties of algebraic objects. One of the fundamental challenges in category theory is the problem of coherence. Coherence addresses the question of when two different ways of composing morphisms in a category yield the same result. In other words, it asks when certain diagrams in a category commute, meaning that following different paths through the diagram leads to the same outcome. The problem of coherence arises because categorical constructions often involve multiple choices. For example, when defining a tensor product of modules, one must choose a specific way to associate the factors. Different choices may lead to superficially different results, but one expects these results to be equivalent in some sense. Coherence theorems provide a way to ensure that these equivalences hold, guaranteeing that the constructions are well defined. Mac Lane made fundamental contributions to the theory of coherence, establishing coherence theorems for a variety of categorical structures. His work provided a rigorous foundation for many constructions in category theory and homological algebra, ensuring that they were free from ambiguity. These theorems ensure that certain diagrams commute, making calculations predictable. A specific example of a coherence theorem is Mac Lane's coherence theorem for monodial categories. A monodial category is a category equipped with a tensor product operation that satisfies certain associativity and unit axioms. Mac Lane's coherence theorem for monodial categories states that any diagram involving only the tensor product, the unit object, and the associativity and unit isomorphisms commutes. This theorem has important applications in a variety of areas, including theoretical computer science and mathematical physics, where monodial categories are used to model computations and physical systems. In essence, Mac Lane's coherence theorems provide a kind of sanity check for categorical constructions. They ensure that the constructions are well behaved and that the results are independent of the specific choices made in the construction process. This is essential for ensuring the reliability and consistency of categorical reasoning. Consider the seemingly simple operation of multiplying three numbers. Associativity dictates that a times b times c yields the same result as a times b times c. This seemingly trivial property is crucial for ensuring that the order in which we perform the multiplication does not affect the final answer. Coherence theorems generalize this concept to more complex categorical settings, ensuring that analogous properties hold even when dealing with abstract objects and morphisms. The implications of Mac Lane's work on coherence extend beyond the technical details of category theory. They touch on fundamental questions about the nature of mathematical truth and the role of formalism in mathematical reasoning. By providing a rigorous framework for ensuring the consistency of categorical constructions, Mac Lane's work helped to solidify the foundations of category theory and establish it as a legitimate and powerful tool for mathematical research. While Mac Lane is best known for his work in category theory and homological algebra, he also made significant contributions to mathematical logic. His work in this area focused on the formalization of mathematical proofs, seeking to develop a precise and unambiguous language for expressing mathematical arguments. This pursuit aligns with the broader goal of ensuring rigor and clarity in mathematical reasoning, a theme that runs throughout Mac Lane's work. Mac Lane recognized that mathematical proofs, as they are typically written, often rely on informal arguments and intuitive reasoning. While such arguments may be convincing to experts, they can be difficult for beginners to follow and may even contain subtle errors. Mac Lane sought to develop a formal system in which all mathematical arguments could be expressed in a precise and unambiguous way, eliminating any possibility of misunderstanding or error. His approach to formalization involved translating mathematical statements and proofs into a symbolic language based on the principles of mathematical logic. This language includes symbols for logical connectives, such as and, or, and implies, as well as symbols for quantifiers such as for all and there exists. By expressing mathematical arguments in this symbolic language, Mac Lane hoped to make them more transparent and accessible to both humans and computers. The formalization of mathematical proofs is a challenging task, requiring a deep understanding of both mathematics and logic. Mac Lane's work in this area was influenced by the work of earlier logicians, such as Gottlob Frege and Bertrand Russell, who had attempted to formalize mathematics using axiomatic systems. However, Mac Lane brought a unique perspective to the problem, drawing on his expertise in category theory and algebra to develop new and more efficient formalization techniques. Mac Lane's work on the formalization of mathematical proofs had a significant impact on the development of automated theorem proving and formal verification. These fields aim to develop computer programs that can automatically prove mathematical theorems or verify the correctness of computer programs. Mac Lane's formalization techniques provided a foundation for these programs, allowing them to reason about mathematical objects and arguments in a rigorous and automated way. Mac Lane's influence extends far beyond his direct research contributions. It permeates the very fabric of mathematical education. He possessed a remarkable ability to distill complex ideas into accessible and engaging narratives, shaping the way generations of mathematicians learn and understand abstract concepts. His textbooks, particularly in abstract algebra, became standard references, guiding students through the intricacies of groups, rings, and fields with clarity and precision. These texts emphasized the structural aspects of algebra, reflecting his categorical perspective and fostering a deeper appreciation for the underlying unity of mathematical ideas. Through his pedagogical efforts, Mac Lane instilled in his students a rigorous approach to mathematical thinking, encouraging them to focus on the essential properties and relationships that define mathematical structures. His impact can be seen in the widespread adoption of his textbook, Algebra, co-authored with Garrett Birkhoff. This book revolutionized the teaching of abstract algebra by emphasizing universal properties and structural relationships. It presented algebraic concepts in a clear, concise, and modern way, making them accessible to a wider audience. The book's influence on the development of abstract algebra as a field cannot be overstated. It provided a foundation for many subsequent textbooks and research papers. The emphasis on categorical thinking in algebra foreshadowed the growing importance of category theory in mathematics. Mac Lane's influence on mathematical education also extended to category theory itself. He recognized the need for a textbook that would make this powerful tool accessible to a broader audience. His book, Categories for the Working Mathematician, became the definitive introduction to the subject, providing a comprehensive and rigorous treatment of the fundamental concepts and techniques. The book's clear exposition and numerous examples made it an invaluable resource for students and researchers alike. It played a crucial role in popularizing category theory and establishing it as an essential tool in many areas of mathematics. The enduring impact of category theory on various fields of mathematics is a testament to Mac Lane's profound influence. While initially met with skepticism by some mathematicians who viewed it as an abstract and unnecessary formalism, category theory has since proven to be a powerful unifying language and tool. It provides a framework for understanding the relationships between different mathematical structures, revealing deep connections that might otherwise remain hidden. In algebraic geometry, category theory has provided new insights into the structure of schemes and stacks. The language of categories allows mathematicians to define and study these objects in a more general and abstract way, leading to new results and a deeper understanding of their properties. For example, the concept of a derived category, which is a categorical construction, has become an essential tool in algebraic geometry, allowing mathematicians to study the singularities of algebraic varieties. In logic, category theory has provided a new framework for understanding the foundations of mathematics. The concept of a topos, which is a type of category that generalizes the category of sets, has been used to develop new models of set theory and logic. These models provide a new perspective on the nature of mathematical truth and the relationship between mathematics and the physical world. Topos theory offers a powerful way to study intuitionistic logic, which rejects the law of excluded middle. This has led to new insights into the nature of constructive mathematics. In theoretical computer science, category theory has found applications in the study of programming languages and algorithms. The concept of a monad, which is a categorical construction, has been used to model computational effects in programming languages. This allows programmers to write code that is more modular and easier to reason about. Category theory has also been used to develop new algorithms for tasks such as data compression and machine learning. For instance, the concept of an adjunction, which is a pair of functors with a special relationship, has been used to design efficient algorithms for data compression. The formalization of mathematical proofs, a pursuit to which Mac Lane dedicated significant effort, has seen substantial progress. His work in this area, informed by the pioneering efforts of logicians such as Gottlob Frege and Bertrand Russell, sought to establish axiomatic systems capable of capturing the entirety of mathematical reasoning. Mac Lane's contribution lay in his application of category theory and algebra to develop formalization techniques that were both more powerful and more streamlined than previous approaches. This work has had a transformative effect on automated theorem proving and formal verification. These fields are dedicated to creating computer programs capable of independently proving mathematical theorems and verifying the accuracy of computer programs. Mac Lane's formalization techniques provided a crucial foundation for these programs, enabling them to engage with mathematical objects and arguments in a manner that is both rigorous and automated. The ability to mechanically verify proofs holds the promise of eliminating errors and increasing confidence in the correctness of mathematical results. Mac Lane's legacy extends to the development of programming language theory. The concept of a monad, borrowed directly from category theory, has become a central tool in functional programming. Monads allow programmers to encapsulate side effects, such as input-output operations, in a way that preserves the purity of functional code. This has led to more modular, maintainable, and testable software. The application of category theory to programming language theory demonstrates the power of abstract mathematical concepts to solve practical problems in computer science. Moreover, Mac Lane's work in homological algebra, particularly his development of spectral sequences, has had a lasting impact on algebraic topology and algebraic geometry. Spectral sequences are a powerful tool for computing the homology of complex spaces. They provide a systematic way to decompose a difficult calculation into a series of simpler steps. Spectral sequences have been used to solve many important problems in mathematics, including the computation of the cohomology of classifying spaces and the study of the topology of manifolds. Saunders Mac Lane's role in shaping modern mathematics is undeniable. He championed a more rigorous and structural approach to mathematical thought, emphasizing the importance of abstraction and generalization. His work in category theory provided a unifying language and tool for mathematicians across different fields, fostering collaboration and cross-fertilization of ideas. His textbooks have educated generations of mathematicians, instilling in them a deep appreciation for the beauty and power of abstract mathematics. He was a visionary leader who helped to transform mathematics into the vibrant and interconnected field that it is today. The lasting relevance of category theory as a unifying language and tool in contemporary research underscores the profound impact of Mac Lane's work. It continues to be a vibrant area of research, with new applications being discovered in fields ranging from physics to biology. As mathematics becomes increasingly complex and specialized, the need for unifying frameworks becomes ever more pressing. Category theory provides such a framework, allowing mathematicians to see the connections between seemingly disparate areas of mathematics. Mac Lane's vision of a unified mathematics, based on the principles of abstraction and generalization, continues to inspire mathematicians today. His legacy will endure as long as mathematicians continue to seek a deeper understanding of the fundamental structures that underlie the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, Please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.